All right, hello. Good evening. Good afternoon. So let me start by a quick introduction. I'm Ivan Martinovic. I'm acting head of department this academic year in computer science department, and it is my great pleasure to introduce to you Professor Srđan Čapkun, visiting us from ETH Zurich, a fellow Croatian. Srđan is a full professor at ETH. He's also chair of Zurich Information Security Institute for Security and Privacy, associate VP for Digital Transformation and Government at ETH, and among all these roles you also do some research, so you just, I believe, finished your ERC Consolidator grant on secure positioning in wireless networks. So his work is at the boundary between the physical and digital domains, starting with analysis of physical layer properties, meaning signal propagation, wireless communication, and actually using physical laws to create security guarantees, such as, for example, something we're going to hear about called distance bounding. And working all the way up through smartphones, sensors, to the satellites and digital infrastructures. Maybe just to give you a quick example, around 2010, we know each other for some time, so around 2010, he published the first paper on vulnerabilities of so-called PCAS system. Now, a PCAS is a passive keyless entry system, not this key, but many high-end cars back then. Now it's more of a commodity, but back then it was quite fancy and expensive to have a key that would allow you high level of usability. Basically, you just need to be near to open the car and enter the vehicle. And Srđan was the first one to have a systematic evaluation of such a system, showing, of course, that there is a logical breakage in design, because ability to communicate does not imply physical proximity. And so he was the first one to introduce relay attacks on that system. Now, that was 2010. When I asked him what the industry has done about it, because as a security researcher, you are required to do this, something called responsible disclosure. So he and his team went to all the car manufacturers, and actually the car industry done nothing, right? They said, well, the usability is a great important sales factor, and these attacks won't happen. Today, you can go to YouTube, there are millions of videos how expensive cars, especially Teslas and similar ones, are basically being taken away in the middle of the night. Interestingly, my neighbor also got his brand new BMW that way. It was picked up by my Ring smart doorbell, but I turned off notifications, so yeah, it was late. Anyway, because the industry did nothing, Srđan created a secure distance measurement system, turned that into a spin-out, a company that eventually later on was acquired very successfully, and today in most of the car keys you have Srđan's secure distance measurement protocol running. Okay, so with this I will stop, and before I finish, a bit of housekeeping. First of all, the Strachey lecture series, our distinguished series, is generously funded by Oxfam, Oxford Asset Management, and we are very thankful for that. And also, please stay after the lecture for some tea, coffee, and biscuits just around the corner here. And with this, let's welcome together Professor Čapkun.
Thank you, Ivan, and thank you all for coming. I'm going to try to cover two topics. One is more kind of mundane and related to smartphones, and the other one is related to maybe our future and cyber-physical systems that will be deployed, and what I believe are the systems that we need to build in order to secure our future, because otherwise I think it's going to be very scary. So let me start with one simple question. And that's, do you truly own your phone? And here, the question is somehow similar to the one that to the test that you can do when you ask yourself, if you truly own a house that you live in, And a good test is to try to nail a picture on the wall. Right? So the similar thing you can do with a phone, you can ask yourself, what can I actually do with this phone? So how much access do I have to what I want to do on this phone? So whether there is some hardware that you want to modify or that you want to configure in some way, you sit over there, so you being the apps potentially that you can develop and install, whereas there is this whole ecosystem below, not only of operating systems, but potentially hypervisors. There is a lot of firmware that's being deployed on these phones. So there is a lot of control that is being exercised, for good or bad, by different entities in this ecosystem. And these could be either big tech entities like Google, Samsung, Apple, Qualcomm, and so forth, or even a lot of third-party entities. And what you can see here already, if you're unfamiliar with the phones, is that the phones are divided into, or at least this ARM platform is divided into what's called the normal world and the secure world, which is typically running something like ARM Trust Zone, right? So that's the architecture. And there you already see a division between secure services and potentially normal execution of let's say, users' code. That part is also heavily controlled by different commercial entities, and as a user, you typically have no access to these secure services. You can't easily configure them. So this is not only about control. So this ecosystem is quite large. We have hundreds of I mean, it's hard to estimate, but there are over 100 million lines of code that your application sits on top of. So even if you have something like a secure messenger running on top of your code, it sits on this large ecosystem of code, which also then results in vulnerabilities being disclosed every once in a while. A lot of them are zero-day, meaning that effectively you don't really know about these vulnerabilities before they are publicly released, but they have been out there in the wild and potentially have compromised your phone. And clearly, with these AI tools coming up that can analyze large code bases, we can expect more such vulnerabilities to appear. This is not surprising or shocking to any computer scientist. This is just a link to some of these 0 days published by Google. So they keep on coming, and so you could even say that at any given point in time, you're probably exposed to some of them on your phone. And they might be weaponized against you, or it depends on what kind of target you tend to be. And I'm not the first one to notice. Reports about security vulnerabilities are everywhere. We can see politicians, people being targeted, also entire organizations being targeted. The same applies to control. In terms of controlling this ecosystem and effectively some of these entities acting as potential gatekeepers to the functionality of the phone. There are numerous reports on this. The latest one you can maybe see by Graphene, for example, which is a secure operating system that you can run on your phone, complaining about attestation being forced into some application ecosystems and effectively breaking some of the functionality on their phones. So this is clearly a problem, right? That we have entities that provide a lot of service. So they create these rich ecosystems, but in some sense, we are dependent on them, right? So we are depending on them to control access to resources, because the way that computer systems are designed is that someone needs to manage access to shared resources like CPUs, memory, peripherals, and so on. And we put this big fat operating system in between, plus other layers, in order to mediate this access. And through a set of privacy security arguments, you can then try to argue why certain access of an application is from an application is actually restricted. So this means effectively that in our today's architectures, access to peripherals such as screens, networks, every sensor needs to be mediated by these OEM operating system providers like Apple, Google, Samsung, and so on. It is not only about control, it's also about availability. So if those entities decide to stop their service, your functionality, whatever that is, would equally stop. And also it's about configurability, which is lack of developer control over what they want to do with the phone. I was involved in a broader effort by EPFL and ETH back then during the pandemic, where we were working on contact tracing frameworks. One of them was in the end adopted and deployed by Apple and Google. And one of our main challenges was just access to Bluetooth and access to Bluetooth beacons. And this was heavily guarded for some good reasons by Apple and Google. And this led to a lot of frustration among researchers, because many ideas that we had, even in that state of let's say, global panic, we could not implement our ideas. So clearly you can run alternative ecosystems, right? You could say, I don't like this ecosystem dominated by big tech players. I'm going to switch to alternatives, and these might be some Linux phones, it might be graphene, it might be alternative ecosystems that give you potentially more control over the phone, but they also have a restricted functionality, because you might no longer be able to run an app that of your bank, or maybe some favorite app that potentially requires a different type of attestation, or wants to be run only within a Google or Apple ecosystem. So this is, you lose a lot of functionality. So this means that we essentially are facing sort of a choice. Either you carry two phones with you, you have a secure phone and a sort of general phone on which you can install some less critical application, or you just suffer with the consequences of each of these ecosystems. So we raised this question some years ago. Why does it have to be like this, and can we actually design something else? So can we have nice things in a nutshell? So a phone that is actually secure, open, developer friendly, and can actually be controlled by the user. But I'm going to refine this statement, because we didn't want full control by the users. We want actually shared control. So this phone needs to be controlled by the user, but at the same time functional and compatible with these large ecosystems like Android, iOS, and so on. So we started this in 2020, started thinking about this, and then published the first paper in 2021. It was a really difficult publication process, I can tell you, because some of the ideas that we wanted to push didn't find immediate acceptance in the community, but effectively we wanted to create a phone that contains several phones, for example 2, where you can run one OEM OS or more, and one or more domains that execute some secure apps. But those apps should have full access to the hardware peripherals. They should be able to run bare metal, essentially. So we wanted to move from this ecosystem on the left, where we have this monolithic, let's say monolithic design, to this system on the right, where we would create ecosystems that are equally privileged. So we didn't want to create a phone where the user dominates these large OEM ecosystems, because this might break their security model, right? So we wanted to build a phone where you can execute your workflow bare metal with full access to peripherals in parallel with the existing commercial phones. And what can you do? There you could create domains, for example, where you run in parallel with, let's say, Android, another secure operating system, or even a self-contained bare metal application that runs directly on the course. So one of these domains needs to be protected from the user. so whatever the user does on the phone and needs to be controlled by the OEM, and others potentially need to be controlled by the user or in any combination of those. So we are talking about really equal privilege, and we wanted to do it in a way that also doesn't over-privilege any of the layers on the phone. And I'll come to the how we did it, but just to set a little bit of a scene, what we wanted to achieve is that we wanted to have secure domains that have direct access to screen and network. So when I'm running in a secure domain, I want full screen access without having to trust Android, for example. So when I'm running in my domain, that peripheral is tied to that code and cannot be modified or inspected by Android. The same with network, for example, or with any other sensor or any other peripheral that we want. Equally, we wanted high availability. So meaning that if Android suddenly drops, that this other domain can take over the functionality and connect to the network and continue running as if nothing happened. So we wanted to remove this dependency on these large operating systems while allowing them to still run on the platform fully isolated from the rest, because the same properties that we want for a secure domain, we also want for the OEM code. And at the same time, we didn't want to introduce a huge layer below these systems and a large TCB, because that wouldn't make sense. You introduce yet another dependency. We also wanted to do it in a usable fashion, meaning that, so how would you now even interact between these domains? Well, this is not a very complicated idea, but it needed to be done. So a simple press of a button, where when you're running your phone, you could just press a button. This button is so that the firmware has been configured such that this button press cannot be interrupted by or modified by any of the running domains. You get into a mode where you can switch between different domains. So either you press a button and you keep on switching between domains or anything of that sort. So at a press of a button, you switch between, let's say, your Android and your secure domain running, for example, a Signal messenger. Right? Why is this? And then you can enable all kinds of interactions between these domains. For example, your Android could be receiving a notification that you have a message in a secure domain without presenting a message, and then you can press a button, switch, and see the message in a secure domain. You can allow interactions between these domains, but clearly according to any policy that you would like. So, of course, all this sounds very, very nice when you present this kind of a vision, and then clearly somehow it needs to be built, or the question is, can you even build this on today's ARM platforms? And what I've learned over these 20 years as a professor is that there is nothing that dedicated PhD students cannot do. So it took us only more than 4 years going through these different prototypes. So first was some ARM board that we worked on. There was an emulator that we used, and then you see there first examples of phones. These were some older phone models that we built. I mean, we didn't build the phones, but a firmware that we updated. And this was in summer 2024 when some hope that this can actually run on phones without much, let's say, much disturbance to the ecosystem. And then finally, in March this year, a spin-off company from our department presenting this prototype at the Mobile World Congress in Barcelona, where we showcased essentially that such a system can be built. And so how does it work? Well, here's the latest prototype, which is effectively from a week ago or so. So a prototype of a phone where you switch between Android to a Linux operating system running some web apps. Trima here that you see is a Swiss secure messaging app, so we ported it there. So every time that you switch potentially to a locked, let's say, a locked screen. Now you switch back to Android, and you can do that as many times as you like, and you can run several of these domains. So that essentially tells you what we built, what can you do. But then the question remains is how? How did you actually build this, right? I mean, what did you do? Well, all problems in computer science clearly can be solved by another level of indirection. This is clearly not me who said this, apparently Roger Needham and a few other people also said this. So the first idea would be to virtualize. You put a hypervisor underneath all these different domains, these operating systems. This hypervisor is going to virtualize access to peripherals, and there you go. This is exactly the path that we didn't want to take. The reason is that you will replace this control that you wanted to give, you didn't want to have within these operating systems with now a hypervisor which will again manage access to these peripherals. So we did not want to virtualize peripherals. We didn't want to virtualize access to hardware. So instead, we wanted to design a lean and simple firmware which will simply connect or dedicate peripherals to different domains. Right? So it is a sort of a simple approach to designing such a system. It, of course, need to be tested because one wouldn't believe that it would actually work without breaking all kinds of functionalities on the phone, but it works. So we introduced a simple layer, and I wouldn't even call it a layer because it's rather a simple piece of code that assigns resources to operating system and domains. It simply says you get these cores at this time, at this point in time when you run, you get exclusive access to the screen, you get this memory, you get access to GPS, you get access to something else. So some of these peripherals can be shared, some of them not, but generally the principle is that we assign instead of virtualize. And ARM actually allows you to do that. So first thing that we did is, if you look at this side here, you see that hypervisors are gone, so virtualization is not needed there anymore, right? This is not something that we want to do. And the only thing that we did is we extended the secure monitor, which runs on EL3. So if you look at these levels, these privilege levels, the EL3 would be the highest privilege level layer here, which we extended with, let's say, 6,000 lines of code, which can then enforce this functionality that I just talked about. And these lines of code are fully transparent and open. Anyone can inspect them. There are no secrets there that one needs. So first thing that we are doing is domains run concurrently on separate cores. So we are not pausing Android, we are not, or iOS. By the way, this works on iOS as well. It's just that access to Apple devices is more difficult than working with Android devices. And so the secure monitor, right, also uses address space controllers in order to assign memory to each of these cores. So it's kind of a coarse-grained access control. In terms of scheduling, one domain, it can be any of these domains, it can be an independent domain, can also be in charge of scheduling the execution of these domains. This also can be configured by the user. It depends on the setup on the phone and the properties that you want. In terms of peripherals, ARM is also pretty good for this in the sense that your peripherals are memory mapped, and now you can essentially use again the address space controllers in order to grant domain-specific access to individual peripherals. So here on this figure, you can see that memory is just mapped so that GPS belongs to this domain 1, and the screen domain 2, and domain 3 runs the network. So maybe this sounds a little bit too exclusive, but when we did the analysis of the peripherals and of the workflows on the phone, it actually works pretty well, in the sense that the screen, for example, is something that you need direct access to and exclusive access to, right? Because when you switch from one domain to another, no other domain should see what you're doing or take input or see what you're presenting on the screen. You also, however, for a network, maybe you can have one domain that you trust for availability, so this domain can proxy the traffic for all the other domains. So you don't need to even worry, let's say, about the network that much if your traffic is end-to-end encrypted, for example. So this really depends on the peripheral and on the configuration that you like. One thing that actually surprised us, and it's always a bit of a over time you refine what you're doing, is what turned out to be the biggest, at least so far, security issue that we have identified were interrupts. So there are a lot of peripherals clearly that work with interrupts, and interrupt management through a general interrupt controller turned out to be the biggest issue. So one of my collaborators, or one of the colleagues on this project, Shweta Shinde, has published a number of works showing how interrupts across different trusted execution environments and so on can trigger attacks on those environments, right? These, you can see them as a type of microarchitectural or side channel attacks. They're not really, it's a different class of attacks, but essentially allowing domains to manipulate interrupts that they are not in charge of causes security issues. So one of the things that we needed to solve, and this turned out to be quite interesting work, was to then introduce this GSE protection, so that we call the GSE guard, that we implemented there in order to make sure that only those domains that own those peripherals can also work with the interrupts from those peripherals. So essentially, that this interrupt routing is protected, that the owners are properly restricted to only what they own. And how this is done, it's maybe a little bit too much of a to get into, but luckily this GSE guard plus the way that the GSE can be configured with these secure, non-secure labeling of interrupts and the awareness of the interrupt IDs of individual cores, you can then isolate this properly and protect your system. So in a nutshell, we created a new architecture. I don't think the core idea is not that new, clearly. Assigning peripherals exclusively to particular pieces of code, I don't think that's a terribly new idea in itself. But somehow going back, or even I would say daring, according to our, given the feedback that we got from the reviewers, to go back and revisit an almost a default idea that we should always virtualize all of our peripherals and all of our resources and then stack things on top of each other. That idea of virtualizing actually didn't really solve the problem that we were trying to solve here, which is a problem of trying to satisfy all the constraints of the users, OEMs, align incentives, and build a platform where we have a minimal, or at least as reduced as possible, level of trust in these common components that enforce isolation, in this case, this secure monitor running on EL3. So with a set of these measures, like the SM, so secure monitor extended with less than 10,000 lines of code, using these memory protection mechanisms to isolate peripherals and memory, extending a GIC guard, essentially extended SM with this GIC guard, reprogramming these buttons, we were able to create an ecosystem where anyone is able to essentially run whatever they want on their phone with full security, isolated from their primary operating system. And I believe that if we can, and we started doing this now, if we can push this to every phone, we can really open up development on each phone, because suddenly these domains get much closer to hardware, and also enable more security and sovereignty on the phone, because now it's up to you to decide how much of the code you depend on for your critical applications. ARM clearly is not sitting let's say, they are clearly developing their platforms. So if you're familiar with this ecosystem, I see some faces here, they are. So ARM CCA, for example, is ARM's confidential computing. These are confidential computing extensions. We clearly then evolved also this design so that if in the future this gets deployed, we already have solutions that would give us the properties that I talked about just on this new platform as well. So yeah, so I'm really hoping that this will go somewhere, and that all of us will be able to have more secure phones, more development freedom, and also we can give users, but also organizations, more sovereignty over their critical workflows, at the same time preserving the benefits of this exciting ecosystem. And I have to say that in terms of the feedback that we got, especially at the Mobile World Congress, and also when talking to people, I'm quite excited that we might be onto something. It's an interesting sort of academic idea that seems to be going now fully commercial. I'm clearly not done with my talk. It's a little bit too early to let you go yet. So this was the first part of my talk where I wanted to talk about something a little bit that touches on all of us, and it's something that we all very often interact with, and made a case for how to make it better. But there is another topic that worries me already for maybe 20 years, but it seems to be more and more imminent these days. So this is most likely, clearly this is an AI generated image, as you can imagine. I asked AI to generate a European city with some robots and drones in it. So this is how AI imagines a European city with some robots and drones. So if you strip out all the technology, it might look really nice and appealing. If you put all the technology in that you see here, it might be a little bit scary, maybe not the future that you want to live in, but it might be the future that we will experience. So a lot of self-driving cars, maybe humanoid robots, maybe drones flying around, delivering things, making our lives generally better. The question that I would ask myself, and maybe it's only me, is if I see a drone flying over my head, or if I see a robot passing next to me, my question is this robot supposed to be there? Right? Is it going to harm me? Is this a friend or foe? And this is a question that I would say most governments and most police forces these days are also thinking about. Are these devices supposed to be there? How do we register these devices? Like we started with cars in a very, very, let's say, loose manner, and now we know exactly where these cars should drive. With these robots and drones, we equally want to know where they are. And are they supposed to be there? So we need to register them. They need to be able to securely and in a verifiable manner determine their location. So, and then potentially report it to us, or the infrastructure needs to be able to measure their location. So what we would actually want is some sort of spoofing resilience, so that these devices, that the locations of these devices can be securely calculated. We want to be able to verify the locations of these devices. And that's a slightly different property because it's about the claimed location of a device that's trying to cheat. And we also want clearly increased resilience to interference because, as we have seen, especially in the case of GNSS, so our GPS, Galileo, and so on, are highly vulnerable to different types of spoofing attacks and jamming attacks. And this is just one of the several maps of Europe where you can see at a particular date, this was in February this year, the locations of where spoofing and jamming is currently happening. And this is not very surprising. If you have been following the news, you might see this kind of news where drones on battlefields are, instead of relying on wireless communication, they're dragging wires behind them in order to be less susceptible to interference because of the interference-based attacks on the functionality of these drones. Now, it's not only the devices that calculate their locations that are vulnerable to these kind of attacks, but it's also the infrastructure as well. So if you read this carefully, you will see that we are already in an era where satellites, especially GNSS satellites, which are quite critical, are seen as a target, and even a physical target, right? I mean, they're even facing potential physical disruption. I mean, this is not very surprising, especially for our group. I think this is a very, very old video, right? Where we were doing GPS spoofing. Not sure how to make this a bit faster, but I'll try. So you will see GPS spoofing happening. So here, this mobile phone is in Zurich, and back then what we did is we spoofed the location from this point where you saw it. It jumped to another building in Zurich. Now it moved a little bit. Now it's going to move to another location. You see it now moving there. This was all done by a spoofer that injected messages into the antenna of this phone, and therefore shifted the perceived location of this phone. And this doesn't only work in a small area. We now shifted the location to Berlin. Right? So this works pretty well. And clearly, this has been done with civilian GPS, where authentication doesn't really exist. So you can generate GPS, authentic-looking GPS signals. This is not only a problem for mobile phones, because as a user, you have corrective mechanisms and you can rely on other markers in order to figure out where you are. But this is clearly also an issue for drones and other robots which rely on this spoofing, on this location information, right? So here you can see I mean, I'm not going to play a video, but this was done by a group of Anjan Raganathan in Northeastern, where they took a drone that was set to hover, and then by injecting spoofing signals, they managed to fully control the drone. So they could essentially order the drone to go left or right by injecting appropriate GPS signals. So why is GPS or GNSS more broadly vulnerable? Well, because first of all, distance, right? It's easy to jam and overshadow and disrupt GNSS signals. These are satellites that are 20,000 kilometers away. The power of the signal at the surface of the Earth is very weak, and this you can't easily fix with that constellation. Another thing is broadcast, meaning that these are broadcast-only signals and they are susceptible to delays, and these selective delay attacks can cause a location to be shifted from one to another location, even if the signals are digitally signed or authenticated in some way, because, well, the adversary can just pick up those signals and shift them to another location or shift them selectively and introduce delays and relays, which has been already shown in academic research quite a bit. Another thing is that the types of waveforms and modulations and time of arrival mechanisms that were built for GNSS, at least for vanilla GNSS, they're not really fully resistant to time of arrival manipulation attacks, and the protection measures do not really scale. So my argument is that we need to rethink positioning. And we actually have a nice chance here. So we are in an age of LEO satellites being deployed heavily. They're much closer to the surface of the Earth, 500 kilometers. We have great experience in running cellular networks at a massive scale. So we can leverage these additional infrastructure abilities in order to secure positioning against both spoofing attacks and interference. And how will we do that? Well, these ingredients, for those who have been maybe following this research, will not be very surprising. So we need to integrate two-way ranging. So it turns out that the ability to do two-way ranging, so round-trip time of flight ranging, can actually solve the problem of secure positioning and of location verification. And also a denser infrastructure gives us more opportunity to rethink our jamming resilience and time of arrival protection mechanisms. So what we are working on is to integrate terrestrial and satellite infrastructure, so meaning work with typically LEO constellations plus terrestrial infrastructure in order to solve this problem. So the first thing that you have to think about in this space, and this is of course a very high level talk, so I can't go into many details, is that, so if you look at the broadcast systems like GNSS, and also like some of the LEO constellations that are simply broadcasting for positioning, you can't really prevent spoofing. So that's really not a solution because of these selective delay attacks that I mentioned. But what you can do instead, you can do round-trip time of flight distance measurements that you can then in addition protect against distance reduction attacks. So if you can prevent distance reduction attacks, meaning that an adversary cannot reduce a distance but only enlarge, it just happens that within this kind of geometry, like this pyramid here, if you do this from several vantage points, you can have a guaranteed provable secure positioning system and even location verification system. So, and this is a result that's quite old. It's from 2004, 2005. Recently, a group of Mridula Singh at CISPA and her student Arslan Mumtaz are extending this kind of an idea with what they call trick, where they are combining essentially a broadcast with a response to, so a broadcast from one of the systems, so for example, GNSS or LEO, and then a response to a terrestrial system forming, instead of these circles that constrain the geometry, they create ellipses in order to and define a region within which spoofing is not possible, right? And into which spoofing is not possible either. So this seems like relatively simple geometric thinking, but there's actually quite interesting academic work behind it. So, but in order for these geometries to work and give us secure positioning, we need something else. We need to be able to protect this two-way ranging against distance reduction attacks. So if we have a satellite and a drone or two drones running challenge response protocols that are authenticated, one would believe that these are sufficient to prevent distance reduction attacks. But they're really not. So we know from the research literature that specially crafted signals injected by the adversary into these two devices measuring a distance can actually shorten the distance that is measured between these two devices. If an adversary can do that, there is practically no help in building a secure positioning system. So we need to solve this problem. So how can this happen? So if you look at above here a pulse which is wirelessly transmitted over a wireless channel, when it arrives at the receiver, it's going to be somewhat smudged, right? So it's going to be spread by this channel because these wireless channels are quite complex. And not only that it's going to be spread, but counterintuitively, the time of arrival of this smudged pulse will not be the strongest peak that you see here, but it might be the one that's before, or you have to essentially determine which one is it. And that's where a lot of crafting might go in terms of building these kind of ranging systems. Which one of these earlier peaks that come before the strongest peak is actually the one that determines the true distance. And by injecting signals in such a way that you can create this even earlier peak, you will be able to shorten the distance. So that's intuitively how this works, not very precise, but intuitively how some of these attacks work. And this was one of the attacks that we did on an ultra-wideband ranging system, where we looked at the ranging between an NXP chip and an iPhone, so an NXP ultra-wideband chip and an iPhone, where when we turned our spoofing, we were able to bring a distance that was measured at 8 meters to 0 meters. So this is clearly, and how did we do that? Well, we actually didn't know any of the keys or random sequences that were exchanged between these two devices, and we injected what was essentially another random sequence on top of the packets that were being exchanged by these two devices, and we managed to cause those early peaks to appear in the receiver and therefore trigger a shorter distance measurement. I mean, measurement of a shorter distance. This is actually a very, very fresh, out of the print result, where we have recently shown, it's a very simple kind of result, again, very counterintuitive. So if you see here on the left, you can use in a narrowband system, you can actually use a negative group delay filter that can, I'm not sure if I have yeah. So here, this blue signal is the signal that should come out of that should arrive at the receiver if we didn't introduce our attack, right? So instead, what we did is we implemented a filter that created this red curve. But it seems as if it has arrived earlier, right? So if you look at this envelope here, and if you measure the time of arrival of that envelope, you will measure an earlier time of arrival. And how did we do that? Well, this filter essentially aggressively amplifies these amplitudes here and then suppresses them later in order to create this shape without knowing what's coming, without knowing which signal is coming. So it's a very, very elegant way to reduce a measured distance by manipulating using, in this case, a negative group delay. Another attack that comes from already from 2006 is what's called an early detect late commit attack. In this case, I illustrated on ultra-wideband, right? Where you have a drone sending some pulses to a drone, and they are supposed to arrive as indicated here. The attacker wants to transmit those pulses earlier, but doesn't know what they are in advance, cannot guess them, right? So they are completely random. So what the attacker can do instead, the attacker can send something in advance, some random garbage within the slots that he wants. And then when he learns a part of the signal that the sender transmitted, he generates the remaining part of this signal. And now some of the time of arrival systems will react in the following way. They will say, hey, maybe half of this symbol is messed up, but the other half shows enough evidence that this is a correct symbol. And when summarized, I think this is a fine symbol. And of course, this kind of behavior that you see here, it's a bit exaggerated, but can happen on the real wireless channel. So you end up advancing again and shortening a distance. So how can one protect against these physical layer attacks? So basic GNSS protections like secret spreading codes can help, not entirely, but they can assist there. There is a lot of work now. There was a work from Apple, for example, in the ultra-wideband space, showing how effectively using spreading codes across different sequences can potentially mitigate some of these attacks in the context of ultra-wideband. GPS is introducing Chimera, which are physical layer markers, which are some sort of punctured codes, right, in order to detect on the physical layer whether signals have been manipulated. In ultra-wideband, we have done a lot of work securing that. Ivan mentioned, resulting in a spin-off company and products. In Wi-Fi, we have mechanisms for that are being now introduced in standards. The same in Bluetooth. And well, that's something that I already mentioned, how this could be done. So in a nutshell, we have different technologies, geometries, and ranges that we could potentially use to derive a position of a device. But at the core of it, for each of these technologies, is how do we protect the time of arrival in order to avoid these kind of time of arrival manipulations? Because at least against distance reduction. Because if we can prevent distance reductions, distance enlargements will be prevented by the geometry itself. So we need to focus on that. And if you look at different technologies that are being used for ranging, you can of course pick on which one you want to work. We worked already on ultra-wideband, on Bluetooth, on 5G, and most recently we introduced a new system that we built specifically for space, so for ranging with LEO satellites, where we then focused on OFDM modulation, because that's a modulation that's being used in a lot of communication systems, including with LEO. And of course, this is now an overloaded slide of all the things that one needs to do in this space in order to make this work, right? From designing the waveforms that you want to use, to designing the packets and making sure that you have a time of arrival verification that's secure and provably secure and so on. I'm going to give you an intuition behind those results. So this is the intuition. Yeah. So what are we doing? For those of you who are familiar with OFDM modulation or not, I mean, it's essentially a frequency kind of embedding, and with an inverse Fourier transform, you get the time domain signal that then you transmit. And what did we actually do? We took two consecutive symbols in the OFDM manipulation encoded in the frequency domain, and we created a verification function that is going to test whether the wireless channel is consistent across those two symbols. And what does this on a high level test? This tests whether the the distortion of the wireless channel is plausible or not. So if it's inconsistent across these two consecutive symbols, this means that most likely there is some sort of an intervention by an adversary and not an expected behavior of the channel. So yeah, and this in this constellation diagram looks like this. So typically when you decode these symbols, what you expect is that due to the channel changing the phase and the amplitude of your arriving signals, you will need to do some form of a compensation. So if you can test that this compensation is inconsistent across two symbols, you can, let's say, build on top of that and then have your time of arrival verification function. And for that, of course, we produced a proof that is in our research work. But of course, security, we need to argue through proofs that we write in papers. But implementation-wise, we wanted to see if such ideas could actually work. And for that, we have built first an in-lab setup, right? This large box here is essentially emulates a wireless signal between the ground and the satellite. So this is a full-blown satellite link simulator, right? Where you can plug in your signals from the ground and from the satellite and back, and then test alongside with all the constellations and all the Doppler shifts and everything that you have to cope with, right? In order to test whether this type of modulation and this type of verification function can actually survive such channels. And we have shown that functionally it can, right? We were not very happy with this because we said we need to go out and actually test this. And then we went to a tunnel because transmitting outside is not so easy if you are getting licenses to transmit in certain bands is not so obvious. A tunnel clearly is not a channel that's representative of a satellite channel. You don't have a tunnel up in the sky, but we wanted to functionally test across 500 meters whether our actually setup works. And so what you can see at one end of the tunnel, there is one transceiver, another one here on this cart, and what you don't see is students pushing this cart down the tunnel, and as a result, you can see this distance actually changing, being reduced as a result of this approach, and then when they pull back, you will see the distance increase back to the And of course, we are not happy with that either. So we did the test in the lab. We did the terrestrial tests, and we will do more open space tests. But we are also happy that ESA will allow us to deploy our design within this cybercube. So there was a competition, and there will be a European Space Agency launched satellite that will implement several projects, including our own, where we will then perform our experiments from the satellite down to the ground. So in summary, I believe that we need to change the way that we work on these positioning systems, in the sense that we need to change the reference that broadcast-only systems are sufficient, that we don't need terrestrial infrastructures to be built in our cities. I think we do. I think we will need more robustness in this space. Otherwise, we will see a lot more attacks that involve spoofing of locations, cheating on own locations by devices. So we need to be ready, build fundamentals for this particular problem space. And if we can do that, maybe we'll have a more secure future. Of course, it's easy to be pessimistic about that, right? Most likely, how these things develop is that you first need attacks and problems to happen and then deploy these kind of solutions. But let's see, maybe we get ahead of a curve. There is some hope because there are already a number of calls by relevant European and global entities calling for secure positioning to be deployed, and also these the effects of the recent wars, where spoofing and jamming has been quite prevalent, are showing how relevant this topic is becoming. So final musings from my side when it comes to generally system design and security research is that I think we can be really bold in hardening our infrastructures. I think it doesn't require us to design everything from scratch. I think we can integrate technologies. Our choice of OFDM it's not only a choice to go for OFDM, but we are clearly looking for integration within existing 5G and other technologies to effectively simplify the implementation of such protection measures into existing ecosystems. In the same way, for the sovereign smartphone, what we wanted to do is to avoid the trap of being exclusive. We wanted to build a platform that's actually open to everyone, including large ecosystems, because this is not a fight against someone. It's a fight to have systems that we can actually control, either as a user or as communities. And so, of course, that I did all of this alone. So these are some of the people that I want to acknowledge that work quite hard on some of these projects that you have seen. And with this, I thank you.